electronic transport to enhance quantum battery charging.
Okay, good. Thank you for the introduction. Just a quick pause. Let me try it out, this one. Okay. I think I'm going to use the mouse. Okay, yeah, this is a different one. Sorry. Hello, everyone. Thank you so much for the invitation, for the organizers and everything. This is my first QEI, so I'm having a great time, so thank you so much. So to begin, since this is my first QEI, I thought that I should self-present myself. I'm a postdoc in Janice Spetz-Stolzer's group. She's over there, kind of hidden behind everyone. We're in Chalmers, located in Sweden. And today I'm going to be talking about a collaboration project which I have between Henning, which is also of our group, and some non-local participants, Federico Cerisola, who was here until yesterday, and Kerry Jovanisian, which I can't see in the room. Maybe he's not here right now, but he'll come. Okay, so to begin, I'm going to be talking about batteries. So my idea, although we heard a lot of things about batteries, let me define first what I consider a battery. So I consider a battery a device that is capable of storing energy and releasing it to perform some kind of work. Okay, so if we go to the classical regime, we all know what a battery looks like. I've never opened a battery myself, but I did a quick Google search and I checked what it was. So a battery, as we know it, is composed of a material, which they say it's an anode, which has an excess of electrons, and a cathode that has a lack of electrons. Continue? Okay. Sorry. So when you connect the material, the anode with a cathode, this generates a current that goes from here to here, and this is due to a difference in chemical potential. So in a way, the difference of chemical potential is what stores energy in the batteries in the classical regime, let's call it. So when you go to small scales, in the quantum part, now the energy is not stored in a difference of chemical potentials, but it's stored in quantum states. So from now on, whenever I say battery, I refer to a quantum harmonic oscillator system. So here I plotted a quantum harmonic oscillator potential, which it has its different energies, and you can charge these energies, and the energy of this quantum battery harmonic oscillator is the energy that's stored. This button, good. So one very important thing within the, let's say, quantum batteries community, if I'm not mistaken, someone correct me, is how to charge these batteries. So this is the typical way you do. You start at time 0, and you have your battery in a chargeless state, let's call it this way. I entered the community quite recently, so I like to refer to real material things. So I think about it as I have my cell phone in an uncharged state. So what I do when I have my cell phone in an uncharged state, I connect it to the battery. So this is what you do quantumly. You have your battery, and you connect it to a charger with some kind of interaction Hamiltonian, and you let it charge with certain protocols that a lot of people dedicate their lives to envisioning, let's put it this way, until some time t. And then at time t, you have your battery at the highest charge state, hopefully, and you disconnect your charger. And then you use your battery for some kind of works or something. So the question here is how much of this energy that was stored in the battery can I use? So what I use my cell phone for is for scrolling to see pictures of my dogs. But anyone can interpret it in their own way. Okay, so the figure of merit is the following. So you start, you can see this, right? Yeah. So you have your battery in this active charged state. You apply some protocols. In my case, I scroll through the phone looking at my dog. But in the lab, I guess, they apply lossless unitary operations. And then you extract as much energy as you can until you get to a discharge state. So I can't look at photos of my dog anymore. Very sad. And this is what they call a passive state after you apply these unitary operations. And then the figure of merit is the global ergotropy. Some people just call it ergotropy, but we call it global, and it would be, later on it will make sense why. And this was already presented, I think it was on Tuesday by Irene, which is basically the maximum work that you can extract from a system. So it's the energy before, when it's active, minus after you extract everything, and it ends up in a passive state, where these unitaries are global in the sense that they extract all the energy only from the quantum battery. And then you maximize over all of these unitaries. And this maximization has a closed analytical solution. And this is the passive state here. which is very good. And then Irene did all her work, and she was able to calculate their entropy. And within the community, as I understand it, there's two main challenges. To say that a quantum battery is usable, in my definition, one, it has to be prepared in an energetically active state. So the ergotropy that you get from the state has to be positive. If it's 0, you're not doing anything. And two, which is, from my perspective, more important, it has to retain the stored energy over long periods of time. Because if I apply this protocol, I charge it, and then I lose everything via dissipation, that's it. So one solution that was proposed in 2020 was charging, but using a non-equilibrium situation. So not to get into much detail, but in a nutshell, what it means is that you have your battery, and you connect it to 2 baths, not 1 bath. One is hot, one is cold. Equally, one can have a higher chemical potential than the other, whatever kind of non-equilibrium situation. And then it gets charged from the time 0 to some non-equilibrium steady state, and the charging is due to the heat current that goes from the hot to the cold, higher chemical potential to lower, whatever you want to say it, to a non-equilibrium steady state. And then you end up in a non-equilibrium steady state, which ideally has ergotropy higher than 0, and then when you want to use it, you decouple and you extract the energy. So how does this solution satisfy the challenges? Well, first, the non-equilibrium steady state can be a active state. So in general, this non-equilibrium steady state can be an active state. And to satisfy the second part, which for me is more important, it's stabilized, because the non-equilibrium steady state is a steady state, so you can't lose it. It doesn't happen because you can't dissipate because there's a bath, because it's charged because of the bath, right? So kind of turning around the game. So we saw this, and it was great. But there's a slight problems with the platforms I studied in my PhD, which is sometimes you can't do this decoupling situation. Sometimes you just have to live with the fact that your charger is always charged to your phone. Let's say this happens sometimes when your phone is very old and you can't disconnect it from the charger because automatically it loses all its battery. So what we worked on is uninterrupted, strong, particularly, coupling with a charging unit. So one clear example where this happens are, as Juan presented on Monday and Natalia, carbon nanotubes that are coupled to single electron transistors. So kind of to recap a little bit what they were. So you have a carbon nanotube. This is kind of here, experiments look here, and theorists look here, yeah? So it's a multi-purpose slide. So you have your carbon nanotube, which is a tube, and it's suspended and it's clamped on both extremities, so here and here, and it's free to oscillate in one direction. So for the theorist, it's just a harmonic oscillator with frequency omega. And this is going to be my battery, so you can call it battery, carbon nanotube, harmonic oscillator, however you want. And then the experimentalists, as they're sitting right there, can say that they add some kind of gate magic potential, and can they find a quantum dot here in the middle, hopefully. And for the theorist, a quantum dot is not much more than a two-level system, let's put it this way. I don't like to call it this way, but it is, with energy mu, which is the chemical potential of the dot. And then the limit that we take is that this is the occupation number of the dot, which can only be 0 or 1. 0 is when there's no electrons, 1 when there's electrons. Voila. So now, due to the fact that the quantum dot is literally inside the carbon nanotube somehow, correct me on this, there's intrinsic coupling that you can't really turn off. And this is called electromechanical coupling. And it's between the occupation of the quantum dot and the displacement of the resonator modulated by some lambda coupling, which the experimentalists work very hard to get a good number. Now, one thing you can know is that this coupling is only on when there's an electron in the quantum dot. So in order to get electrons in the quantum dot, what the experimentalists do is they supply to the left and the right some kind of bias. So one is usually to the ground, the other one they supply with electrons. And this way they generate a disbalance between the reservoirs. In this case is a chemical imbalance. So due to this chemical imbalance, meaning that the left reservoir, the source, has a higher chemical potential than the right one, under correct conditions, there we go, electrons can jump from the left to the right. And this generates an electronic current through the device, and it's how do you say? And it's also non-zero in the steady state. And whenever, due to the electrochemical coupling, whenever an electron jumps from one side to the other, it supplies the harmonic oscillator with some energy. Yeah? So what is now our protocol? Very similar to before. We start in a state where the cell phone battery is 0. I can't look at photos of my dog. And now we connect everything, and we let it evolve. And we let it evolve to a steady state. And as theorists, what we do, we model it with a Redfield equation. So we go to the steady state at infinity time. And now we have an extraction stage. And this is the crucial part, which I'm going to try to go as slow as possible without losing time. In this case, we don't want to uncouple to the charger, right? So we only want to extract energy from our battery, not from our charger. But we have to maintain it coupled. So the unitary that we have to apply to the system is of this form, where we don't do anything to the charger, and we apply some kind of work output to the oscillator, battery, whatever you want to call it. Okay, so what's our figure of merit now? Because we can't use this global ergotropy. I think now it's obvious why I was calling it global, because the unitaries here act on, oh sorry, this should be a system, my bad, but act on the entire Hilbert space of the system. So what we do with uninterrupted coupling is we look at the local ergotropy, which is a subset of these unitaries. And it's only the ones that have of this form, where they don't do anything to the charger, and we only extract from the battery. Now, in principle, as opposed to before with the global one, this one does not have a closed analytical solution. There are some cases, and I only know one case that it does, but in general, it does not. So what we do in our work is derive suitable bounds. So we have an upper bound, which is motivated by the average occupation of the quantum dot. For interest of time, I'm not going to go into that, but just believe us that there's an upper bound, and a lower bound that we obtain numerically. So under these circumstances, what are the relevant questions? The first relevant question, wow, this is huge. The first relevant question is, under what charging conditions can the energy be extracted from the quantum battery? That is to say, under what conditions is the battery a battery that's holding energy and we can extract, as opposed to doing nothing? Second question, how does this continuous coupling affect the battery storage? Is it better, is it worse, what happens? And then the third is it even advantageous to remain coupled? Because we could have just uncoupled it somehow in one way, experimentalist problem on how to do it, and is this even better? Okay? So for the remainder of my time, I'm going to answer these questions. So for the first question, what I'm going to do is consider a constant coupling, let's say 2.5. These numbers don't mean anything for now, but we'll see later. And what I'm going to do is vary the chemical potential of the quantum dot, which we saw in Natalia's talk, that experimentalists can do this easily. And the reason why we do this is to look at the different charge states of the quantum dot. So what I'm going to show here is this is what the sweep in the chemical potential. So for example, if we're in one extremity, we put down the chemical potential of a quantum dot such that there's no electronic current. This is the electronic current. And the electron is stuck in there, so there's no current. The other limit is the opposing limit, where the chemical potential is all the way up and no electrons can come in the quantum dot, so there is no current. In the middle, there's the famous Coulomb peaks, where is the electronic current that goes down. Now, if we go in the bottom to see what happens to the battery, the harmonic oscillator, the dashed line here is the lower bound, and the solid line is the upper bound. So in the two limits where the electronic current is 0, so the electron is either stuck or there is no electron in the quantum dot, we see that there's zero ergotropy. So here it's not really working as a battery. But if we look here in the middle where there was electronic transport, we see a non-zero ergotropy. So here's where it's working as a battery. So the conclusion of the slide is that work extraction is achieved only when there's electronic transport. Yeah? So this answers the first question. Going to the second question, is what happens with this coupling, right? So what we do now, is we grab the maximum mu for different couplings. So here I sweep in coupling from 0 to, I don't know, 3.5 to say something. The ultra-strong regime is defined as this green box, let's say, and we see a non-trivial behavior where there's a maximum at 2.5. So there's kind of like a trade-off between the coupling and how much you can extract from the battery. This is what it's telling us. And then kind of for reference for the experimentalists here, I put some previously reported couplings. There is another coupling from the ICFO group, but it's a lot more. So it's outside the plot, just to emphasize that we know that that is also existing. Yeah, so these couplings say, so our maximum in a way says that it's within the regime of actually experimentally achievable couplings. Motivation for the experimentals. Now going to the last question, is it even advantageous to remain coupled to the charger? So for this, what do we compare? What do we compare with and without, right? So here on the left, I have the situation that I was talking about before, the continuous coupling scheme, where we see that there's some ergotropy under some situations as a function of lambda. Now, to know if it's advantageous or not, the kind of spoiler is the title, we're going to compare it to the case where we actually decouple. So now, the unitaries are applied only to the quantum battery. So our figure of merit is the global ergotropy that I was talking about before, but we have to be careful now because there's an energy that we pay when we decouple. So as opposed to before that we didn't decouple, we don't have to pay this energy. So if we compare the local situation of continuous coupling with decoupling, paying the price, and seeing what we get out, we see that it's always negative. So what it tells us is that we always pay more than what we get when we have to decouple, as opposed to before, in the continuous coupling scheme, that at least it's positive. It's small, but it's positive, so at least we gain something. So now coming to my final slide, what I presented is an experimentally achievable, oh, sorry, there's a typo, but there's an experimentally feasible nanomechanical model of a harmonic oscillator continuously coupled to a quantum dot acting as a charger. And we establish a concrete pathway to recycle that energy that otherwise would be extracted, because these kind of experiments happen all the time. So it's kind of to make aware the experimentalists that, okay, there's something that you can actually extract, even if you're running an experiment, just running your nanotube to see what's happening. So in a way, this is kind of a proof of concept. So to answer the three questions that I posed, one, under which condition can energy be extracted? We saw that work extraction is achieved when the quantum dot hosts electronic transport, so only when electrons were flowing from the left to the right was it acting as a battery. For the second question, how does the continuous coupling affect the battery storage? We saw that it was a non-trivial trade-off between the charging and the coupling. And to finish, is it advantageous to look at this, or should we just abandon all our work and go back to this global ergotropy decoupling and stay with those protocols? Yes, it is advantageous to at least consider these kind of protocols and study into it. So with this, I think it's my final slide. Yeah, it's my final slide. Thank you for your attention, and I'm open for questions and feedback.
Thank you, Sofia, for the very nice talk. Can I ask a very quick, maybe stupid question, and then I let you?
You're the chairess, so you choose.
Can you go back to the slide where you explained the first question?
This one.
Yeah, I understand that, you said when there's zero electron transport, there's no, the device is not working as a battery, but I think you didn't comment on the fact that there's like a bay exactly where the electron transport is maximum. So can you develop on that?
Yeah, so kind of on purpose. So we're studying into exactly, I didn't specify why, because so there's two answers to this question. One is the honest question, which is we don't know yet. We're still studying into it and seeing what's happening. And I can give you the second question, which is my personal intuition, is that here, this is the point where you're referring to, right? This is where the population being occupied and unoccupied is the same. So in a way, it works kind of like a symmetry. Okay. Yeah, and we know that symmetries sometimes have particular effects, let's call it this way. So in a way, my intuition is that it's having this effect, but we're studying into seeing exactly what's happening there. Yeah, we're almost done, but we have a little bit of details to finish.
Okay. Thank you.
Yeah.
Who else?
Thank you, Sofia, for the talk. I have a few questions,
Sure.
and let me ask two. First of all, how many electrons are allowed to occupy the quantum dots?
One at a
So-
time.
Okay, that has been a secondly. And why are you talking about autonomous work extraction? What is autonomous here?
Yeah, so autonomous in the way, so maybe I can go back here's where I put the word for the first time. So there's many ways to charge batteries, right? Some ways are applying specific unitaries and hoping that your final state is a specific one, which is an active one. That's one way. In this case, we say autonomous in the sense that you connect it to the bus, you let it run, you go get a coffee, you come back and it's charged. In this way, it's autonomous charging.
Does it depend on time or not?
Well, yes, I mean, you have to wait until the steady state, but experimentally, the steady state is actually quite fast.
Yeah, but it's not autonomous in this case because
No,
if
it's autonomous in the way that you're not perturbing it. You're not applying protocols. You're not applying certain unitaries. So the protocol is connected and go take a coffee. And that way it's autonomous.
Okay, thank you. And the last question.
Yeah.
Why it's experimentally feasible?
Well, great question. So first, we basically use the same Hamiltonians that have been proven to model the carbon nanotube system. So in that way, we're not doing any new Hamiltonians or anything different. So in that way,
but Natalia is doing classical experiments. So
yes,
far.
yes, so far in a way, but from my understanding, they can access quantum, and Marta is nodding in a way. So I think that depends what you call quantum.
There are no coherent interaction in their setup.
Okay, what I call quantum is a relationship between the tunneling rates, which I didn't write here, and the frequency of the battery. But we can discuss this later on because it's like very particular. Yeah, it's related to previous work, so we can discuss this later.
Okay, thank you for your answers.
Yeah.
Maybe quick question.
Si.
Is it hard to estimate the variance of the charging?
No. I mean, experimentally, not sure. But theoretically, no, because you have the state, so
Right.
you can.
But experimentally, you can derive the state as well, more or less a description.
If they do quantum state tomography, yes.
Alright.
I mean, they can calculate probability functions, so you can calculate the Wigner function. But to go from the Wigner or Husimi or whichever one they choose to variance, I'm not sure.
No, that I can do it, but
Okay, if you can do it, that's great.
if you can do Wigner, I'm satisfied.
Okay.
All right,
Yeah.
thanks.
I go or thanks, Sofia. So if it's too technical, maybe we can discuss later. But
Sure.
I didn't get if you can start work just when you pass from 0-1 chair, the state, or when there is transport. Because have you ever think to define like a double quantum dot, and then in one dot you pass from the state 0-1, but through the tube you don't have transport?
Yeah. So it's when you have transport.
Okay.
This kind of depends on timescales, right? What turns off, what thermalizes first, and stuff like this. So we were discussing a little bit, kind of to give numbers to experimentalists how to do it. But in principle, the theory, let's say, it's when you have transport through. And indeed, when you have a double dot, everything is kind of different. Yes. Yeah. Yeah.